In this video, I'm going to show how Newton proved Kepler's second law. Kepler's second law states that if there are two sections of the orbit that take the planet the same amount of time to travel, then it will sweep out the same area. In this diagram, you can see that the red and blue sectors are shaped differently, but they will have the same area as long as the times taken to travel along the perimeter are equal. You can see that when you have a ball swinging around on a string, your fingers have to pull the string in towards the center of that circular path in order to maintain the ball swinging around in a circle. Here again, you can see the ball is traveling around in a circular orbit, but the force is going towards the center of the circle. The case of a planet orbiting a sun is similar. It's different, however, in that it's an elliptical path instead of a circular path. But still, the force, in this case the force of gravity, is going to go towards the sun, from the planet to the sun. Here the sun's located at the focus of the ellipse. A focus is simply one of the 2 points, one of the 2 foci that define an ellipse. The sun is located at one focus, and you can see the planet has a gravitational force that's pulling it towards the sun, which sends it into this elliptical orbit. The way that Newton proved Kepler's second law was by breaking up the elliptical path into a series of triangles. This is a diagram from the book that we need in order to do Newton's method for proving Kepler's second law. I think if you haven't taken geometry in a while, it's not going to be obvious right away why these 2 triangles have equal areas. So to help you remember how to find the area of a triangle, I drew 3 of the same triangle, and there are 3 different ways of finding the area. You can see any of the 3 sides of the triangle can be called the base. I could call that side the base. And then the height is simply defined as a right angle. So in each of those, the area is 1/2 base times height, regardless of what you call the base. It's a little more difficult to find the area of an obtuse triangle. You can see I'm calling that the base, but that would not be the height on the right hand side. You have to go 90 degrees from the base, so I'm just making a 90-degree angle from that side, which I arbitrarily called the base. And it's not clear how far you go to determine the height of that triangle. So what you have to do is draw an auxiliary line, which is that dotted line, which is parallel to the base. The auxiliary line and the base are parallel, and then you just continue drawing up, and then that's the height of the obtuse triangle. Back to this figure in the book, we have 2 obtuse triangles. It says that the base AB and BC are the same. They're obtuse triangles, so again we have to draw an auxiliary line, and then for that first triangle we're going to figure out the 90-degree and then draw up to the auxiliary line, and then that is the height of the first triangle, SAB. We do the same thing, 90 degrees to that second base, draw it to the auxiliary line, and then that's the height of the second triangle. You can see that those heights are the same. If you measure them, it should be, exactly the same height. The bases we already said were the same, so therefore the areas of the 2 triangles must be the same. Next, you need to know that 2 vectors, such as these 2 arrows, D1 and D2, if we add those together, we can just slide them so that they're connected like that. D1 and D2, same direction, but we just slide them together, and then the resultant vector connects the tail to tip like that. The planetary orbit also involves vectors, because in the first section the planet's traveling from A to B, and it would tend to continue in a straight line towards small c, according to Newton's first law, which just means that bodies in motion tend to stay in motion in the same manner. However, as we'll recall, there is a centripetal force which is acting towards the sun, which is labeled S. That centripetal force is going to kick the planet over in that direction, down towards the lower left part of the paper. So I just slide that vector up to point C, and then you can see that the planet's actual path is going to be from B to large C, like that. So this complicates the proof a little bit, because we have to prove that these different triangles are the same in order for Kepler's law to be true. Remember, Kepler's law is saying that each sector, if it's a same amount of time, is going to sweep out the same area. So really, to complete this proof, we have to prove that red triangle has the same area as the triangle SAB. And to do so, we're actually going to prove that SB large C has the same area as SB small c. You can see that those two triangles have the same base, SB. That should be very obvious. Those two triangles have the same base. Now, if we can show that they have the same height, we'll prove that they have the same area. So what we do is we draw an auxiliary line which is parallel to SB. This auxiliary line that I just drew is parallel to the original base, SB. Since those are parallel, we can define the heights by just doing 90 degrees to the base for both of those triangles. So for the first triangle, we're going to draw the 90-degree point up there, and then when we trace the height, it's going to be from there, the auxiliary line, all the way down to the base. So that's the height of triangle SB capital C. For SB small c, we also do a 90-degree angle up to the auxiliary line, and then you should be able to see that the two heights are the same. Since the heights are the same and the bases are the same, the areas of those two triangles have to be the same. So this proves Kepler's second law, because at the beginning we said that AB and BC took the same amount of time, and now we just showed that all those triangles have the same area. So Kepler's second law, again, is that if the planetary orbit section takes the same amount of time, it will sweep out equal areas. And as the planet continues to move, the sun will continue to bend its path. Ultimately, it will add more and more sections like this, and if you can imagine shrinking the triangles down extremely small, it'll be a smooth curve. It'll be a smooth elliptical orbit for which each sector has the same area.